We're finally going to get into atomic structure in Chapter 7, and to do that we have to take a brief stint into the electromagnetic spectrum because we study structure by looking at how it interacts with light, amongst other things. So a little bit about the electromagnetic spectrum here. True or false questions. Blue light has a shorter wavelength than red light. That is true. X-rays have lower frequency than radio waves. That is false. X-rays are smaller, so they will have a higher frequency. Microwaves have higher frequencies than gamma. That is also false. Gamma waves are smaller, gamma rays, so they will have a higher frequency, shorter wavelength. And then visible light composes the major portion of the electromagnetic spectrum. That is very false. It is just the tiniest fraction of the electromagnetic spectrum. And then one of the equations we need to use here is going to be the speed of light is lambda, that's wavelength times frequency. So some night vision devices use infrared to create an image, and if the infrared radiation has a frequency of 1.7 times 10 to the 12th inverse seconds, those are hertz, what wavelength does that correspond to? Well, we know the speed of light is 3.0 times 10 to the 8th meters per second. We do not know the wavelength, but we know the frequency is 1.7 times 10 to the 12th inverse seconds. That will give me a wavelength of 1.76 times 10 to the negative 4th meters. And since the speed of light's in meters per second, we just need to watch out for unit conversions there to make sure that those match. And then 1.76 times 10 to the negative 4th is a lot longer of a wavelength than visible light, so we can kind of navigate that's in the infrared range, at least so that it's higher than visible light, or longer. And then we can do some stoichiometry with that as well. We've got our other equation is going to be the energy equation. What is the energy of light? And that is Planck's constant, h, speed of light. hc over lambda is probably the version that's most useful because it relates the wavelength to the light. But that's just substituting the other equation. On your equation sheet, I think you only get energy equals Planck's constant times the frequency. But the frequency is equal to the speed of light over the wavelength. So we can see that those are the same thing. But hc over lambda, a little bit more effective. Sodium atoms have a yellow color when they are excited in a flame. The color comes from the emission of light at 589 nanometers. Now that is a wavelength, but we need that in meters. The easiest way to do that, nanometers is 10 to the negative 9th. Let's just call it doesn't have to be in standard scientific notation to go in your calculator, 589.0 to get sig figs right, times 10 to the negative 9th meters. All of a sudden we're in nanometers. So the frequency, or the energy rather, nope, the first one asks for frequency. What is the frequency of this light? Well, 3.0 times 10 to the 8th equals the wavelength. I'll put this in scientific notation here, standard scientific notation, 5.89 times 10 to the negative 7th meters. That is a standard exponent, 10 to the negative 7th power. That means you have 100 nanometers, 10 to the negative 9th, which is very typical of visible light. So if you see that, just kind of be aware that that is what it stands for, and you'll start to recognize when you have visible light by those things. The frequency then is going to be 5.09 times 10 to the 14th hertz inverse seconds. Okay, what is the energy of this radiation? Okay, so the energy then is going to be hc over lambda. Now I'm going to use this equation because they gave us the nanometers and I don't have to have my last problem right to to make sure that this is right. 6.626 times 10 to the negative 34th joule seconds. That's the Planck's constant. The speed of light is 3.0 times 10 to the 8th meters per second. And my wavelength is 5.89 times 10 to the negative 7th meters. So the energy here is 3.37 times 10 to the negative 19th joules. Also a very common exponent for visible light. Now, it looks like the units there are joules, and they are, but there's an implied unit here as well. So this is where the stoichiometry is going to come in just a little bit. We need to watch units and unit conversions. This is the energy of the single photon of light that's emitting this yellow color. A single photon. So it says here in the problem, and I kind of ignored it, but let's look at it specifically. Per photon. Well, if we have an individual photon of light at that wavelength, 589 nanometers, that's one photon. So there's an implied unit here. This is the energy of light. This is the energy of one photon of light at that wavelength. There's one photon there. So if you catch that, then you won't be surprised when you get to this question. How much energy do you get per mole of photons? Well, a mole is just a very large number of photons. And we have Avogadro's number to help us with that. So if this is the energy of one photon, I have a mole of photons. So it's pretty common that we'll go back into Avogadro's number, 6.02 times 10 to the 23rd photons. That's a mole. Okay, if I have that many of them, how much energy can I get? Well, every single one photon we just calculated is 3.37 times 10 to the negative 19th joules. So that gives us a way to just scale it up. One of them gives me 10 to the negative 19th joules. A mole of them is going to give me 203,167 joules. Now that does not register on the joules scale, and sig figs, let's just take care of it, 203 kilojoules. Okay, 203 kilojoules. Okay, so then we take a look at this problem. This one is just going backwards. It takes 382 kilojoules of energy to remove 1 mole of photons. So there's the unit conversions here. 1 mole of, to remove 1 mole of electrons from gaseous cesium. What is the wavelength associated with that? Well, we need to know that 1 photon of light, if I have an atom, there's my nucleus and there's my electron shells. If I have an electron in there, if I have 1 mole of electrons, that means I've got this single photon. This is my one wavelength, my one photon here. It's going to come in and interact with this atom. There's a 1-to-1 ratio there. So every photon interacts with an electron. What we're trying to say is if I have a mole of electrons, I really have 1 mole of photons as well. So I need a mole of photons to interact with those. So 382 kilojoules of energy. Let's get that back into joules. And then we have 382,000 joules per mole of electrons or photons, whichever one, because it's they're equal. And then every 1 mole is 6.02 times 10 to the 23rd photons. Okay, so this allows me to cancel the moles out, and we divide this to get back into our energy. And now we have 6.35 times 10 to the negative 19th joules. 6.35 times 10 to the negative 19th joules. Now we can just plug that into our energy equation. So our energy equation, hc over lambda, and since we're asking for the wavelength, that's why this version is just more helpful. Let me erase that here. Great. So 6.35 times 10 to the negative 19th joules. There's my energy. Planck's constant, 6.626 times 10 to the negative 34th joule seconds. Speed of light, 3.0 times 10 to the 8th meters per second. And that will give me a wavelength that is in meters. My wavelength then is going to come out to be 3.13 times 10 to the negative 7th meters. Now remember what I said about that exponent. We want to kind of figure out where this is in the electromagnetic spectrum. Visible light is our guidepost. So we want to kind of compare everything to visible light. So let's compare this to visible light, which is on the nanometer scale. That negative 7th is really saying I have 313 times 10 to the negative 9th meters. Okay, just kind of unstandard scientific notation, which, if that's how many meters I have 313 nanometers. You can do a normal conversion, but I'm just kind of showing you some visual ways to look at it. That is a smaller wavelength than our visible light. So if I'm a little smaller than my visible light, which kind of ends at 400 in the purple range, this is definitely in the ultraviolet range. So we can answer that question as well. Okay, not that that was part of the question, but we can kind of translate and see where that falls. This last equation is actually one that was taken out of the College Board, of the AP class, but we just kind of want to show you because it's still useful in terms of like understanding why these things happen. So this equation that we don't need to know, if you want to put your pencil down, we don't really have to be responsible for it. The mass of an object actually has a wavelength that's associated with it. This is kind of the implication of Einstein's famous experiments. With some other scientists, they kind of combined their work, and instead of saying speed of light, because objects that have mass don't travel at the speed of light, we can find the wavelength of objects traveling at any velocity. So we say v, not frequency, but velocity. Our mass here, if we kind of look at this, 9.11 times 10 to the negative 31st kilograms. And we're going to leave that in kilograms because that's my joules SI unit. That's in joules. Equals Planck's constant, 6.626 times 10 to the negative 34th joule seconds. Proportional to my wavelength, or I'm sorry, divided by my wavelength and my speed. And my speed, velocity, is 5.31 times 10 to the 6th. So not traveling at the speed of light, but electrons move really, really fast. We look at this and we get a strange kind of answer. This electron that has a very tiny mass and is moving very, very fast resonates at a frequency of 1.37 times 10 to the negative 10th meters. Now I show you that because that exponent is very telling. This is about how big atoms are. So this wavelength property of electrons and protons and neutrons, it really matters on the atomic scale. So they actually do resonate at the frequency that they exist on, which gives us some strange phenomena that, like the wave-particle duality, matter acts like waves and Light has mass, these very strange things. But that kind of wraps up the electromagnetic spectrum portion of this, and then we'll jump into the atomic structure next.